millimeters. Oh, and then that arm OA is 160 millimeters. And the pin is part of it. And then we have the guide. It sits right in here like this. And then this is part of a mechanism that's pinned down here. Call that body D. Okay, so there's our geometry. And we've given member D a clockwise angular velocity of 1.5 radians per second. And this is omega of D, clockwise. Determine the angular velocity of member, this is labeled OA. So we wanted to get omega OA in that configuration. They show this other little arm hooked on here, but that's immaterial to the problem. They suggest, they say, do the problem either graphically or geometrically. Suggestions? What's the path of A? What kind of path does pin A have? Everybody see it? Path of A is a circular arc about O. You should see that. Okay. Just for the fun of it, what about A prime?
So does the prime always where it starts, you just like inscribe it at the point that it starts?
Coincident with the point that's moving on the other body.
Okay.
Okay, just for the fun of it, A prime's still going to be right there, isn't it?
What about point C?
Excuse me? But hooked on to member D, right?
Yeah.
Yeah. So it's sitting there, and it's hooked on to member D, right? So what's its path?
Around point C.
Around the point, which I didn't label, C. So it's around this radial arm here. So the path of A prime is like this. Now, given that this body D is rotating clockwise, then that means that A prime is moving down here, right? Where my finger is. Which means that point A is back on the inside of it. So the relative velocity of A prime relative to A is back towards what? A prime relative to A? A moves down to here. A moves down to here, new position, while A prime is now out there, right? Right? So A prime is the velocity of A prime relative to A is outward directed. Or if you reverse those, the velocity of A relative to A prime is inward, back towards O. Okay.
Along member AO.
Along member AO, yes. Okay, now they said use either geometry or graphically to determine this velocity. Given this geometric configuration, 80, 80, 160.
I look at the angle COA, name that angle some theta.
Okay, so you're going to define this as some theta. And so what we're looking for then is this omega, the theta dot term here. Okay, good.
We
Okay.
have another angle.
Yeah, so what we have, let's see, extra sketches are sometimes useful. So we've got that, our geometry.
Find a geometric relationship between that angle theta and the angle of CA off the horizontal.
Okay.
There, yeah. V or
So-
whatever you call it.
Let's redraw this. Here's our defined points. And so we define this as theta, and why don't we call this one beta? Theta and beta. Okay? And if we can figure out the relationship between those time derivatives of those angles, then we've got a relationship to nail down the OA value. Okay? Good.
It's not asking us to solve it. It's to solve it generally. fast.
Geometrically. Now, we've got to be a little careful here. C connects to what point? Does it connect to A?
No,
C really connects to
Just the slot.
A prime.
A prime, doesn't it? C connects to A prime. So this thing is CA prime. And this member is AOA or AO. So let's see. Let's just write up some geometry relationships. There might be different ways of doing it here. Something I'm saying is that this horizontal distance right here is equal to 160 cosine of our theta. And this distance right here is going to be this 160 cosine theta minus 80. Right? 160 cosine theta minus 80.
Which nicely equals
Excuse me?
CA cosine beta.
And, well, and then what I'm seeing is that I've got a tangent relationship for beta here. Right? Okay. So I'm seeing that the tangent of beta then is equal to 80 divided by the horizontal leg right there, which is this thing. All right. Now, does anybody see some simpler relationship between theta and beta that we might be able to utilize instead of this? I don't know if I have a solution printed out from the answer manual or not on this. Anybody see any other geometric relationship that would help us?
I think it isn't fundamentally different from that. One, can you define?
Use the 160 and the 80 to solve for the entire length of that bottom. And just a number.
160 and this 80?
Yeah. Solve for the entire length and then.
Well, that would be a numeric value.
Yeah, and then you subtract,
Yeah, in a 1-to-2 ratio.
and then you subtract 80, or the full length minus the 80, and it'll give you
Okay.
that small length.
But we have to allow for variability.
Yeah, that would only be for what is it?
Well, yeah, but then you can get the hypotenuse from C to A, and you can write a relationship between beta and that length. So you can.
Okay, but remember, this length changes, does it not? Doesn't that length change over time? Yeah, CA prime changes over time, doesn't it?
CA changes over time.
Oh, CA, yes, CA, thank you. CA prime stays fixed. Okay. For the oblique triangle in there?
Well, there's the two different equations, the one that relates to the theta and the one that relates to the beta. There's the two different types of
Okay, so Pam,
cosine equations.
which triangles would you want to?
Really,
Oh, I see what you're saying. You're suggesting that we use the law of cosines involving theta here and this length,
Yeah.
and to have described this length, and then come in here and use this little triangle. There's a sine relationship, 80 over that. Okay?
Well, there's also the law of cosines with the angle that's outside. So instead of the
Here.
minus, it's plus.
180 minus beta
Yeah.
in here, and use this.
No, it's
No, to
using
find beta instead of subtracting.
Oh, I
in the
just
law
thought of,
cosine.
I just thought of something. Remember, I started out saying there's a variety of ways, and one thing I saw was what I developed here. And then through your just comments, here's one that I think might be useful, is if we would use this 180 minus beta right there, and then write a law, oh darn, I was thinking a law of sines involving these two, and then I wanted to use this and this, but I don't like that. I was trying to avoid using that leg. Tell you what, what I'm wondering about is, let's go ahead and go with the various triangles that you were just commenting on, you folks. What were you thinking there, Julie? Let's go ahead and see if we can write that up.
Well, I think what Pam was saying was
Yeah.
there's the two laws of cosine. So there's one using the theta, which is minus.
This
Right.
one involving these two legs,
Yeah, is it that? I think it actually might be.
side, angle, side. That would
Yeah.
give us an equation for this length,
And that length is changing, right?
and that length does change.
Okay.
Hold it.
But if we, we might be able to substitute
Yeah,
that like that.
OA changes. Let's write that. I mean, that's something that's useful in itself. Let's write that. So using the triangle OAC, law of cosines is telling us that CAC squared is equal to 160 squared plus 80 squared minus twice 160 times 80 cosine of theta. AC changes with time. Okay. If we differentiated this with respect to time, we're not going to be needing that in this. I don't believe we'll use it in this problem. But what we would have is we'd have twice AC's length times the time derivative of AC with respect to T. And that's going to be equal to your 320, your negative 320 times E times negative sine theta, theta dot. So if you, your battery, you okay back there with sound? Yet or not? Got it? Okay. Everybody okay with this? So what is this derivative right here? What's
The velocity at which A is approaching C.
yeah, yeah. Okay. But that's not giving us the stuff that we need for the problem, is it? Okay. Now here's the law of cosines we just wrote for AC. Now what was the other triangle you wanted to try?
I was thinking with beta, and then there's the law of cosines where instead of -2 times.
You want to use this guy?
Yeah, and the same law of cosine, same
You
triangle.
want to use the
that angle.
okay? You want to use this 180 minus beta?
Yeah, I was
And-
thinking the other beta, but that one's probably. I think that one's better because then. you
And that
have
would be
the
involving
length
this
of
leg
the
side
slot.
angle. Let's see. Or this one. Or this one.
Yeah, I was thinking that
If
one
we use
maybe
this one, do you want to?
use-
What relationship do you want to use there? You want to involve AC again?
Well, you can use the 160. You can use the OA.
This one and
Oh, yeah, but then that one, you have to use the
Yeah.
CA prime, and you said you didn't want to use that, right? Because it's
Right.
changeable.
Well,
if I still use that same triangle, if I use the same triangle and I use the 180 minus beta, let's see how that would set up. That would set up as 160 squared is equal to 80 squared plus AC squared minus twice 80 times AC times the cosine of the angle opposite the 160, which is 180 minus beta. But cosine of 180 minus beta is the same as minus cosine beta.
you could sell.
How did I know that? Little trick of the trade. If you have a unit circle, imagine you have a dummy angle beta who's on a unit circle whose sine is here and whose cosine is there, right? If you visualize 180 minus beta, that angle is going to be sitting here. This large angle, right? 180 minus beta. So here's the sine of the 180 minus beta. And here is the cosine of 180 minus beta. How does this length relate to that length? They're identical, except one's the negative of the other. So this collapses to that. It's a nice quick way to do those kind of things. And you can do that oftentimes as long as you have relationships like beta plus 90, beta minus 90, 180, 270, those standard 90-degree multipliers tagged onto one of your angles. So rather than using your difference formula. Okay, I don't like this.
Give you a nasty substitute.
It's not a nice substitution to try to get a relationship between, get the AC out of here and get a relationship between theta and beta. Okay, but I was fishing. I wanted to sort of see what ways you folks might go on it. I think we only have a couple minutes left. Let me see if I have this in my solution set, number 89.
Could we use a law of
Let me, I'm in interest of time, let me just see if I'm trying to see if I can get this wrapped up. Here's what they did. How much time? I got 2 minutes left is all. Okay. There's another class in here today. That's the reason I wanted to, sorry about rushing on this. Tell you what I'm going to do, just to keep you in suspense. I think we're just going to, I don't think I can do this in 2 minutes. So I think what I want to do is I'll show you what they've done first thing in next class session then. Okay, and I think you'll find it useful. Okay, so we'll let it go at that. Keep firing away at things. Try to get up into this relative velocity homework problems. So, because we want to start on instantaneous velocity, center of zero velocity, and then also the relative acceleration stuff probably on Thursday. Okay.